Okay, good afternoon, everybody. I hope everyone's having a wonderful day. So today I'm going to be first picking up where I left off last day. Last day I was showing you how we can take any old context-free grammar and turn it into something called Chomsky normal form. So our goal was to take any arbitrary context-free grammar, put it into the so-called Chomsky normal form. Recall that it had the following forms for all their productions, where you can have so-called non-unit productions, but it has to consist entirely of variables. Or it could be a production where I have only one symbol, a unit production, which only consists of a terminal. Or it could be that I have the start symbol and I'm allowed to produce this epsilon over here. So these are the three types of production rules I would like in my Chomsky normal form. I must stress that S here is the start symbol in my brief review here. And of course, B and C cannot be the start symbol. So last day I was up to about step 4. There's 5 steps in this process. The last one I used to delete all the epsilon productions. So these are ones that consist solely of epsilons. In all of the rules associated with variables that are in fact not the start symbol. So recall I had to do a series of operations to get here. Each one is its own algorithm. But I'm actually at the very last step. And it involves getting rid of these nasty ones. Notice right here that I have these variables over here. I have this one, and I also have that one. Notice that these do not fit the Chomsky normal form over there because I'm allowed to have a terminal on the right-hand side of a production rule by itself, but not a variable, So I need to do something about these. I need to eliminate them. So fortunate for us, there is a rule to do this, and it's not too terribly bad. But so let me just describe this to you first, and then I'll kind of give you the intuition with this. So remember, we're looking at the unit rules that have this form where it's a variable, it produces another variable like this. Now, the intuition I want to give you here is just that whenever you see a single variable in a production rule on the right, in the body of one, well, what does that mean? It's going to have to follow down to another production rule for that variable symbol, where that's going to be the head of the production rule. So for example, x0 here, notice that x0 here is the head of a production rule, which will substitute or produce 0. So the idea is I would like to get rid of these production rules where I have the bodies with a single variable. So what I do is I look at what that variable exactly means. So and then what I do is I substitute that variable for what is actually present in the one for which there is already another string that represents it. So just to be clear, what we do is we remove A produces B, and then whenever you encounter B produces a something, where U is just some string of terminals and variables, what you're going to do is you're going to add a production rule, A produces U. So remember, U is a string of terminals and variables. So keep in mind, I'm kind of describing this a little bit more broadly so that you could use this separately. But that being said, only add it if it wasn't deleted before. So obviously don't add something you already got rid of. And then what you do is you keep doing this over and over again until there are no more unit variable productions. And that's it. That's the step. That's the step. So does everybody understand what we're going to do? We're going to try to get rid of this, this, and this. We have those 3 right there. Now keep in mind, depending on what order you end up doing these, you may have to repeatedly apply what I've just described here. So for example, actually our example here, it isn't the greatest one for this, but generally the idea is that you keep repeatedly applying this. But notice that if you say we're thinking more generally about a context-free grammar and I just applied this rule, it could be that U consists of itself of another production rule where its body is another variable. So what happens is you end up dragging up a whole bunch of just single symboled variables that are in production rules. So you can, it will feel very much like you're dragging them up using this process. So that's one way this plays out. The other one, and this is the one that you have to be careful about, is you'll notice that I have this A here. And I want to get rid of that. So what I did was I'm supposed to remove S0 produces A, and then you're going to replace that by all of the production rules where you had, so you're going to basically look at this. Remember, I say, okay, so wherever B, so now B here is A. So it's saying, okay, wherever B produces a string occurs, you're going to add a production for that. So this is one of the reasons why this step, you want to try to incur and use it towards the end if possible. This is why I'm giving this one actually as the last rule. So you'll notice that I have to copy, I have to take this one and I have to add it in there. I have to take this one, I have to add it in there. I have to take this one, add it up there. So I'm basically copying this entire row and putting it up here. So you have to be careful about this. So does everybody understand that? So there's kind of two ways that this eliminate unit production step actually plays out. Is that it could drag up variables, causing this to happen several times in a row. Or it could be that you have to copy a whole row of productions, because the head happens to be the one that you're trying to get rid of. So if there aren't any concerns about this, let's go to our example and let's try applying what I've just described here. So let's go check that out. So I've got, let's walk through this. Fortunately, I wrote this in advance. It makes things a little easier so I can talk to you while okay. So from our example we have over there, these are the three that I isolated out for you. So recall, we don't want these. So notice that X0, it's ahead of a production where I can produce 0. So what I do is I replace A1. So I place this, A1 produces X0 with A1 produces 0, because I'm just taking out the string. That was where X0 goes. I just substitute it in. I do the same thing with B1. And then what I have to do is I have to copy that entire row for the head of the productions A. So I have to go through each one, and I'm going to have to add that to a production rule where it's S0 produces each of those in that row. So you're going to end up with this, and this is, so you're going to end up with S0, so X0, A1. So I'm just putting this where A was before. X1, B1, 1, 0, and then recall I had this epsilon kicking up over there as well. So that's how I resolve this issue. So all I do is I just copy the row of A. Now keep in mind that it's still here, so I have to make sure I still keep this here. I didn't get rid of these rules. They have to stay here for now, unless I get rid of them in the future, but I'm not. 1, 0. So this is where A went, is I used the rule, right? It says, okay, well, I get rid of S0 produces A. And then what I did was, okay, well, what's A? Okay, so A can be producing this, it could produce this, it could produce this, or it could produce this. So I have to go and add in for each one, S0 produces X0 A1, S0 produces X1 B1, S0 produces 1, and S0 produces 0. So that's how I resolved this last one here. And now I'm going to just take care of the rest of these. A1, and I have AX0 like before. And recall, the way I resolve it up here is I just simply replace X0 with a 0, because that's it. All I'm doing is I'm just putting it up there. Throwing it like a ball. A1, sorry, A, X1, or 1. So notice I'm just doing the second one right here. And then lastly, I have X0 produces 0, X1 produces 1. Now I have a question for you. Is this in Chomsky normal form now? So remember the form. And I'm glad I wrote this down here. So notice that everywhere on a production rule, now we have two variables. None of them are the start symbol. On the right-hand side of the production symbol in each one. Or I have it where it is the head of a production rule produces some terminal symbol. And of course, we're allowed to have the epsilon sitting up by the start symbol or start variable. So now it's in Chomsky normal form, right? So this is in Chomsky normal form. So we're done. Wonderful. Wonderful. Now, I do want to make a remark about this, because you might ask, Dan, the way you described some of these steps the other day, and including this last one I just mentioned, you described them in a way such that you could even apply them in a different order. And that is indeed something I wanted to suggest to you, is that there is a way to do this. Now, I must stress that the way I've suggested that you do them in this specific order is a rather nice way of approaching this to get the Chomsky normal form. You end up with where if you were to count up all the symbols in the original context-free grammar, so if you count up all the symbols in the productions, and you asked, okay, well, how much bigger can the grammar be for this Chomsky normal form? It could be no more than about big O of n squared of n was the total sum of all the characters or symbols that are in all your productions. So it's no more than quadratic. It only blows up by a quadratic amount, which is quite nice. That's a nice property of applying in this order. I must stress that there are other orders that you can use. So you can apply step 1, step 2, step 3, step 4, step 5 to get that quadratic blow up. However, it's very real and possible that you can apply them in a different order. And you may ask, which one was the one that causes this thing to blow up the worst? It's in our process, it was actually the final step. Notice how I had to copy an entire row of productions? That could happen a lot. So that's where that quadratic blow up, most of it's going to happen. It's that last step. Now, if you do not, for example, reduce the lengths of these production rules early on, and you do it much later on, or you may remove these epsilons at a different stage, they do affect how big this can get. I will stress for you that there are ways to do this in a very bad way. And if you find yourself using or reading the Sipser book, they have an ordering in there where they do it in a different order than the way I presented it to you. I use the approach of Hopcroft, the Hopcroft book. In the Sipser book, the order they give you is very intuitive as well. It's the same things I've just described here. They just changed the order of them, just ever so slightly. And ends up, the one that gets out of this one actually blows up to, like, it could be potentially exponentially larger. So I only warn you that the order that you do these actually really does matter, but there actually is some flexibility for the order in which you apply these to get a Chomsky normal form. So I just want to stress, so when you think about Chomsky normal form, I recommend using these 5 steps. So if I ever asked you to turn it into Chomsky normal form, we'll follow the 5 steps I've given it here. But I do want to open your mind to the idea that you can apply these rules in a different order. Sometimes it works to your detriment. So just think about it logically as you apply them. But I do want to mention this approach, it also does exist, but the blow up or the size of the grammar actually gets quite a bit larger. That's why I'm recommending that you do it in this sequence. Are any questions about all this? So this is all I have to say about Chomsky normal forms. It's a very nice, simple form. Remember, like I said, if you think about the parse tree, it'll have the form of a binary tree, which makes it nice and easy to represent. Because everybody seems to like binary trees, right? A lot of people seem to like binary trees. And I also did put another example. So for those that haven't seen it, there is another example of doing this Chomsky normal form conversion in the notes if you haven't seen that one before. Okay. Okay. Okay, so there's a couple of things. So the first thing is that, like I've mentioned last day, when you have, so that's a wonderful question. So this is about the advantages of using a Chomsky normal form. So first, the simplicity of this structure, this very nice simple structure, allows you to encode it in a way that's easier for everybody basically to understand. So for example, there do exist parsing algorithms or certain algorithms that rely on the grammar being in a certain form. So for example, I'm trying to remember the name off the top of my head. I think it's CYK. One of these algorithms requires that the grammar is already in Chomsky normal form. But yeah, no, we may talk about this actually a little later on when we start getting towards the end of talking about context-free languages. But like I said, the form of it makes it very easy to encode. So you don't have this general like waviness of the structure of the grammar. Instead, it actually has a nice simple form so that you can easily know and control how the parsed tree can work out. It doesn't really resolve ambiguity. That's one thing I do want to point out, is that it doesn't resolve ambiguity because there's always going to be languages where there's never going to be a nice unambiguous grammar. But this is one step in the nice direction where you have a little bit more structure to work with, and there's a procedure for you that you can actually convert any context-free grammar into this form. So if anybody ever needs you to say, hey, look, I need the grammar to look a certain way, the Chomsky normal form provides a nice simple structure for doing things. A lot of programs, a lot of programming languages and that, they rely on you be able to describe them in a nice simple way. Likewise, obviously we're not going to be dealing with the ambiguity issue. That's more of something you have to keep in mind when you're doing these kind of things. But this nice simple form allows you to encode the context-free grammar nicely. But yeah, there's many things I could enumerate. This isn't really a compilers class, but there's most certainly things about compilers that relate to the Chomsky normal form that are of a benefit. But yeah, I really like that question. But yeah, it's such an open box where I can go start whittling into things and we'll have no time to talk about anything else. But yeah, no, I really like that question. Wonderful. But yeah, the first thing I can think of is just to encode the grammar is so much easier when you have it in a Chomsky normal form. Because now you never have to worry about these long bodies or some weird snaking thing going on. Now it always has a very specific form. So that makes it nice to use for algorithms, because then the algorithm will have some specified behavior that you can always know in advance, so you never have to worry about any weird edge cases. Wonderful, wonderful. Okay, so that's all I have to say about Chomsky normal forms. That was a wonderful question. That's actually a perfect way for me to end this topic. So let's I want to switch gears. Not literally, but more figuratively. I want to talk about some way we can talk about context-free languages, but I want to kind of revisit the idea that we can kind of think about the languages more algorithmically, like we were earlier in the course. Because the context-free grammar is great because you can describe all sorts of languages using it. However, wouldn't it be nice if I had some way of describing the languages like I did before, where I had this, we had like the finite automatons and so on. We had all of these earlier on in the course. So wouldn't it be nice if there's some way I can describe context-free languages in a way like that? So that brings me to talking about our next topic, which I'm actually kind of excited to talk about with you. So our next topic we're going to talk a little bit about, maybe the next couple lectures, is Pushdown Automata. So you might ask, Dan, is this going to be kind of like the finite automaton version of the context-free languages versus the DFAs, NFAs, epsilon NFAs we had for the regular languages? The short answer is yes. But I want to work there. I want to work up to it. And you might ask, Dan, if we're trying to model things that are supposed to represent computation, you might ask, how exactly are we going to buff up the power of this finite automaton? And now, let me give you two ideas of how we're going to do this. So let us consider a more a more descriptive, I don't want to insert anything at this stage, a more descriptive finite automaton with two main ideas. So I'm going to take these two ideas and slam them together with two main ideas. So the first one is I'm going to take the most descriptive finite automaton I've shown you so far. That would be the epsilon NFA. So imagine I give you an epsilon NFA. Remember, we have all those epsilon moves, and we have the non-determinism that we can take advantage of, where we have a set of states. I would like to take this, but I want to introduce something that's a primitive form of memory. So last time when we talked about finite automatons, we had this idea that, okay, well, there's only so much memory the finite automaton is capable of having, right? Where we have a state and maybe we can take advantage of some repeating states over and over again. What I would like to do is I would like to actually introduce something that's actually a primitive form of memory. And this is something fundamental to any computer that you might think of when you think about everything from, say, running functions on a computer program to all sorts of other things. So here's a very primitive type of way of allowing us to have a little bit more to work with, is naturally a stack. So now I'm going to give this finite automaton a stack to play around with. So that's the bump up I'm going to give it, is I'm going to give it a stack it can work with. So I'm going to have a stack, and I'm going to tell you that this stack can store strings of stack symbols. So I'll define what those mean in a little bit. So we're going to have these stack symbols, and all of the intuitions you have with a stack, whether it be pushing and popping on a stack, that's going to be exactly present here. So I'm going to be formally giving you this idea of how the stack is going to operate in a moment. So I just want to draw you a fun picture, just to give you an idea of just the intuition behind this. So I'm going to imagine I have this stack. So here's my stack. Isn't it a beautiful picture? And I'm allowed to have as much memory for the stack as I like. So I don't have to worry about it being some bounded size on this stack. It's going to be, I'm allowed to have an infinite amount of memory, which sounds kind of magical, but another way you can think about it is just that there's no end of the memory I can ever use for this stack. And then I'm going to have this finite state control. And the finite state control, its job is going to be to consume symbols. So so our notion of reading a symbol is going to be more about, it gobbles it up, kind of like a really hungry cat or something. Which will take in the input, and it will read it just like what you think of for a finite automaton, and it will tell you if it accepts or rejects. So I just want to give you just a little intuition with this. So I want to give you just kind of a list of features that you can think of when we think about the pushdown automata. So the first thing I want you to think about, so here's just intuition before I get a little bit more formal about what this means, like what a pushdown automaton is. So just some intuition. So I'm going to tell you that we have something akin, meaning kind of like, or sort of, or similar, akin to a finite state control. A finite state control. Finite state control that reads each symbol that reads each symbol of the input. One after the other. So this isn't too much different, right? Remember, we always read the symbols. We had it like left to right, and we read them, and then we did some transitioning, right? One after the other. Now, this is where things are going to deviate quite a bit. So, the pushdown automaton can also peek. That means it's going to be able to look at the top of the stack. Can also peek at the top of the stack. At the top of the stack. And then on transitions, you're going to really have two possibilities that can happen. So let me just note this down here. So on transitions, either you're going to have the first possibility. Now, it's okay if I write the rest on the next board? So, wonderful, wonderful. Okay, great. So let me move on over here. So let me just note this down, because I want to give you some intuition with this, because I'm just giving you a heads up. I remember when I first learned about Pushdown Automata, and I just remember seeing all the symbols that were involved with this thing, and it kind of spooked me. And then it made a lot of sense as soon as I started playing around with it. I don't want that to happen to you. Or at least I want to prevent that from happening. And say if you're not so inclined with seeing all the crazy symbols. So I just want to give you an intuition, because it's really, like, if you got the idea of an epsilon NFA in your head quite well, and you just think about it like that this machine has the ability now to push and pop symbols off a stack, you're in a good place. So let me just write down that part. So there's going to be kind of two things that can possibly happen here. Either it depends. It depends on the current state. An input symbol. Remember, that's not too much different from our epsilon NFA. We just have some state and some input symbol that we read, right? That's not too much different. And then there's this other fact that kicks around. And the symbol on the top of the stack. Or here's another thing that could happen. Another thing that can happen. It may transition. For free. I'm putting that in quotation marks because I'm not being formal about this. For free via epsilon as input instead of an input symbol. Instead of an input symbol. So that isn't too much different from the epsilon NFA, right? We're allowed to transition, essentially, like I said, for free on an epsilon move, right? We have our epsilon transitions or epsilon moves. But you're going to see how the epsilon plays along with this stack, and it changes up things quite a bit from what we've done before. So when a transition happens, what's going to happen? Let me just describe this more high level, and then when we get to writing more formally, I'll write down this process for you. So just for dramatic purposes, I'm just going to pretend I'm reading this just like that. There we go. So what it's going to do is, on a transition, it's going to consume or process a symbol. And if And if it doesn't consume a symbol, that means it's going to use epsilon instead. So just like what you could think about with the epsilon move. Now, next, it may possibly move to another state from there once it consumes that symbol or uses epsilon. And then, naturally, it might replace a symbol on the top of the stack. Now, there's kind of three things that can possibly happen when I do this. So there's three things that can happen. So the first one that can happen when I have my stack is the top of the stack. The top of the stack is replaced with epsilon. So that's the first thing that could happen. This is going to be the equivalent of popping it. This is popping the stack. And make sure you use the correct number of P's and O's here. Okay? I have to be that way. I'm terrible. This is popping the stack. So if you encounter, when you have a transition for which an epsilon occurs for the stack symbol at the top, it means it's going to pop the stack. Another possibility is that the stack may not change. The top of the stack is not changed. That's another possibility. And the third one, of course, is I can push symbols onto the stack. In fact, I can push one or more symbols onto the stack. Or even the string. So this would be the string that I pass along for symbols. The string may have one or more symbols. One or more symbols. Which may push multiple symbols onto the stack. So we have two things going on. We have transitions between states, and along with this, we're going to have it where we allow symbols to get pushed or popped off the stack. So we're going to have both of these things combined for our pushdown automata. They're not two separate things. They're both integrated parts, actually. So when I tell you, oh, there's transitions and there's a stack, the way the transitions are going to be defined is they're actually going to be defined simultaneously. So I'm going to have transition on a state, and I'll be able to peek at the top of the stack, and they'll tell me what I'm supposed to do next. So this stack will operate it's basically it allows it to remember stuff. And when based on that memory, we're going to allow us to do things with context-free languages. That's going to be our idea. So I just want to give you just an idea of what exactly I can do with this. Is it okay if I move on over here? So I just want to give you a high-level idea, and then we're going to formally define the pushdown automaton. And then we'll see if we have time to formalize the example we have that we're going to do next here. Because I'm just going to first just kind of give you an idea, just to give you a flavor, just before we get a little too formal about this. Just want to keep it high level. Because I find at first when you see these things, it's like, oh yeah, but once I show you eventually a transition diagram, I'll be like, boom, that makes sense. But I just want to build up to this properly. So I want to consider an example. Let's consider an example. Now, this is one of the first ones we've encountered where we showed that it actually wasn't regular, right? This is the first language I think we proved this was our first example where we proved a language wasn't regular, right? So consider the following language. This is where I have an equal number of zeros and ones. So you might ask, Dan, how can I use a pushdown automaton to recognize this language. So here's an intuition. This is just an intuition. I'm going to draw you a picture just to illustrate the idea. And then I'm going to formalize it depending on how much time we have. If not, we'll do it next day. So that's just the general game plan. So here's an idea. Here's an idea. Break it into 3 parts. So I'm going to have, actually, in particular, we'll say 3 parts, but they're really going to be phases. So maybe let's try this. Here's an idea. So imagine, remember, you have this stack. You have a stack. And before you think about the pushdown automaton, I want you to think back to, if you've done any programming in a while, how you would naturally try to use a stack to determine if there's an equal number of zeros and ones. So here's an idea. And then I want your input on this. So first phase, I'm just going to read zeros for each one. For each one, push a stack symbol. Just push a stack symbol and say I'll call it X. So for example, if I had a string, say 0, 0, 0, 1, 1, 1, the idea I have, this is my intuition with you, and I hope I can convince you that this is a nice idea, is imagine I have this string here, and I have it so that each time I read a 0, I consume it, so I'm done with it. So each time I do this, what I would like to do, so I must stress that technically in a pushdown automaton, you don't necessarily have it where it's going to be, where you're going to have some start symbol sitting right here. So I won't worry about that at this stage. I just want to use the idea of a stack that you're familiar with from data structures. So what I'm suggesting we do is every time I see a 0, I consume the symbol. So I've consumed this. And every single time I do this, I'm going to push a symbol. I'm going to call it X. So I have a question for you. If I want to do, let's say, another phase here and proceed to read ones, so we're going to read some ones possibly. What should I do when I am reading ones? Pop it. Exactly. I love that. That's exactly it. So every single time, so if I consume this symbol, what I do is I pop this. So I pop it. And I consume another symbol, I pop it. And I consume another symbol, I pop it, right? And then my stack is empty, right? So naturally, you know exactly when you have an equal number of zeros and ones. It's when the stack looks empty, right? Read ones. So of course we pop the stack on each one red. And then naturally, like I just said, as the wonderful suggestions would suggest, is that we just want to check if the stack is empty. If the stack's empty, then we're good, right? Then we accept. But notice that I can phrase this in a little bit of a different way. Notice that I always push X's. Yes, what's up? Yes, so this happens. So this happens after this process. So what'll happen is we'll even have an option to move the phase 2 if we aren't reading any zeros. So what'll happen is I could for free move from phase 1 to phase 2, and I can also move for free from phase 2 to phase 3. But I want to only be able to do it when the top of the stack's going to look a certain way. That's where we're going to go with this when we get a little bit more formal about it. Because the only information I have about the stack is actually what the top of the stack looks like. So I just want to allude to the fact that, yes, so these 3, so the idea is that and this is something keep in mind, when you think about these phases, this is very much how you would approach it if you're actually doing this in like a programming language like C++ or Java or something. This is a way you could do it with a stack, right? It's something that you definitely probably could implement if you're familiar with one of these languages. Is you just push, and you can push one of these symbols, and if you end up with a stack that's empty, then you're done, right? But yeah, this third phase is quite simple. If there are no x's on the stack, and then of course you accept. Otherwise, and at any, now you might notice in this process, I never told you when to reject. You'll notice that quite quickly if I read more symbols, or I read a symbol that isn't what I'm anticipating. I must stress that these steps are, the first two phases are optional, right? Because I could read some zeros, or I could read some ones, but notice that I need some mechanism that gets me to go from here to there and here to there. That's where the pushdown automaton is going to come in. Is I need some way to go from here to there and there. So I need some way to know this. Now, in a conventional programming language, you have ways to do this. But we need some way of doing it with only certain information. Because remember, we're using the stack to help us remember stuff. So, does everybody understand the general idea? Because when we get to formalizing it, I will walk us through how this actually looks when we actually do it. I just want to kind of recall to doing this. So this would be something that you could do, like, say, earlier in your studies. You would have done it as a programming assignment or something, or even on a lab or something. So you're already seeing things that match stuff that you probably have seen or tried to do before in your past, which is kind of neat. If you think about it, it's like we're already at something that we can actually just express something that actually uses a data structure that you may have seen before. So now that brings me to my point where I would... So now what I would like to do is I would like to define the pushdown automaton for you. And depending on how much time we have, we'll see if we get all the way through or we get to our example. If not, we'll do the example next time. We'll revisit that example. So now I need to give you the definition of a pushdown automaton. So I'll abbreviate this as a PDA. So if anybody ever tells you, like, oh, in the theory community, they tell you about a PDA, usually they're talking about this. A lot of theory around compilers is built around these PDAs. By no means should I be the one to tell you that, yeah, this is like the only way to think about PDAs. I must stress this. But here's the definition we're going to use. And like I said, don't let the symbol spook you, okay? So a PDA P is a 7-tuple. Means it's going to have 7 parts to it. 7-tuple P is equal to Q sigma gamma, that's new, capital gamma. Then we have delta. And we have Q0. We're going to have this one called Z0 and F. I told you, don't worry, it's okay. I've only added a little bit more to what we had before. So, I have to define all these things for you. Some of these are going to be just like what we talked about with an epsilon NFA. Others are not going to be. So, where you might naturally think the Q is a finite set of states. That's exactly right. It's a finite set of states. So that's what Q is. No different than we had before. Sigma is a set of input symbols. Not any different yet. Now this gamma, I have to tell you what gamma is. Now, you might ask, what is a gamma? This is going to be the set of all your stack symbols. So you're going to think of gamma very much like sigma. So sigma was all your set of input symbols, right? We normally had it like zeros and ones and stuff like that. Gamma is going to be the symbols that you're going to use on your stack. So these are going to be symbols that you push and pop onto the stack. This will include a special symbol called the start symbol. So I'll talk about that later. So gamma is a finite stack alphabet. Some people like to call them just the finite stack symbols. So this is sometimes called the stack symbol. Sometimes it's called the stack alphabet. So I say this is the set of symbols that can be pushed onto the stack. So these are the symbols that we're going to use to manipulate the stack. So just like in my example I had before, I had the symbol X. This would be, for example, an example of a stack symbol. So that's what gamma is. Now, this is where things are going to get a little fun. Well, Q0 is really easy, right? You might already guess what that is. That's just the start state. Sorry, I'm getting very excited about this. Q0 is the start state. So not any different from the epsilon NFA. So far we've run into just this that's a little different. Okay. Next, I'm going to tell you that there's another start-like symbol, and it's called usually the start symbol. So just like what you might think of if you think about the context-free grammars. So, sorry, I just about wrote F, I mean capital gamma. So Z0, capital Z0 is in gamma, is the start symbol. So now you have a start state and a start symbol. Is a start symbol. So at the beginning, a PDA has a stack where it has one instance of this symbol. I'm going to reiterate this because I'm kind of cramming it all in one corner here. So Z0 is in gamma. It's called the start symbol. At the beginning, a PDA has a stack where it has one instance of the symbol. So at the very beginning of this process, so when I drew my stack over here, this one, the way you want to look at it is that Z0 is just going to be right here at the beginning. So this will be the top of the stack right here. So Z0 will just be right there. And that's how it's always going to be. Is the start symbol is going to be representing the top of the stack right at the beginning. So I have enough to, actually I have a quick question. Is it okay if I take 2 minutes of your time just to wrap things up with this definition? It's just only one little thing I have to define for you. And I've already given the intuition for it. So let me just quickly write it down. I think we're okay. Let me quickly jot that down. And then we can get to our example next time. We'll actually have a couple of examples, at least. So let me tell you about the one parameter there that I did not tell you about yet is delta. Actually, no, I have to tell you about the final states. The final states. Let me tell you about that. So of course we need F. This is exactly what you think of in the epsilon NFA. F is the set of final or accepting states. So this is no different than we had it in the epsilon NFA. Accepting states. And now I'm just going to define the transition function, then I'll tell you a little bit more about it next time, okay? So delta is the transition function. Where delta is a triple. So now it's a triple. It's not just a pair now, it's a triple. It's a triple where delta is 3 parameters, Q, A, and capital X, where Q is a state in Q. A is an input symbol, not too much different, just we have this extra one, is an input symbol, or epsilon. Remember, epsilon is not an input symbol. That's no different than the epsilon in FA. And the final one is the stack symbol. X, which is in capital gamma. So next class, I will tell you about what the output of this transition function looks like, and then we'll do our examples, okay? So I want to say thank you very much, and I'll see you next day, okay? So have yourself a beautiful day. I'll see ya.